All right, hi everyone, and welcome to another CBRG session. So today we're going to go over how to perform hierarchical clustering and plot heat maps in R. So just a quick introduction to hierarchical clustering before we actually start to plot the heat maps. So to begin, let's take this example data set. So this is a really simple data set which has just 6 genes, genes A to gene F. And 2 samples, sample 1, sample 2, and you can see that there are some made-up expression values. If we were to plot these data, it would look something like this. So sample 1 against sample 2, we can see the gene expression values for A, B, C, up to F. And you can see, just by eye, that there are 2 clusters forming. One cluster of ABC and one cluster of DEF. Another way of visualizing this is to perform hierarchical clustering. So this is the output of hierarchical clustering, what's known as a dendrogram. And we can think of this as an upside-down tree where the genes form what are known as the leaves. And if you compare this to the previous image, you can see that gene A and gene C are the closest to each other. And so you see gene A and gene C, they form their own little cluster. And then you can see that little cluster of gene A and gene C is then close to gene B. So gene B forms a cluster with the cluster of gene A and gene C, and so on. We build up these clusters. When I say, when I use the word close, I mean in this specific case the Euclidean distance. So that's simply, if you were to draw a straight line, how long is that line? And this is known as a dissimilarity metric. Now, there are others that we can use, but Euclidean distance is the most common one. And so we get this dendrogram. Now, one thing with hierarchical clustering that's different from other types of clustering approaches is that we don't need to specify beforehand the number of clusters we want. So, for example, for k-means clustering, we would have to specify beforehand if we wanted 2, 3, or however many. So this is a nice approach because it gives you, just gives you this, this diagram. And you can then, looking at it, decide how many clusters there are in your data set. And this will be informed by the particular experiment that you're running. So in this case, this is very artificial. It looks like there are 2 clusters. And so looking at this, we can see that one cluster contains ABC and another cluster contains DEF. And the way we separate a dendrogram into clusters is by drawing a horizontal line at a certain height. So if we were to draw a horizontal line at, for example, 1.5, this would split our dendrogram into 2 clusters. One thing worth mentioning is we mentioned that to form a cluster, like a mini cluster of like A and C, we just compute the Euclidean distance between those 2. But what if we wanted to do, what happens when we try to compute the distance between this cluster, this mini cluster of AC and gene B? What does it mean to compute a cluster between, compute a distance between a gene and a cluster? So there are many approaches. One approach is this thing called complete that we can see here. So we can go through some of these approaches and and their details. This text has been taken from an Introduction to Statistical Learning by James, Witten, Hasty, and Tipshirani, which is the Bible on introductory statistics. So complete means that you compute all pairwise dissimilarities between the observations in cluster A and the observations in cluster B, assuming you have 2 clusters. And you record the largest of the similarities. And so that's, as I said, this is a common linkage approach. Alternatively, you do the same thing. So the single linkage approach would be doing the same thing, except you record the smallest of the similarities. For average, you record the average of the similarities, and centroid is this dissimilarity between the centroid for cluster A and the centroid for cluster B. Now, why should you choose one over the other? That unfortunately depends on the task at hand, but a good default, and this I believe is the default for hierarchical clustering in R, is to use the complete linkage. And that's in fact something that these authors recommend anyway. But it's good to know that these other linkages exist, and importantly, if you switch complete to single or complete to one of the other linkages, you are very likely going to get a different output. So this is important to know. Before we move on to the coding part, let's consider this issue of scaling. It's very common to see that you don't actually use your raw data to do your hierarchical clustering or plot your heat maps, but instead you use the scaled version of those data. So once again, let's take a simple dummy data set to try to understand why it's a good idea to scale, or it might be a good idea to scale. So once again, we have genes A to gene F, genes A to F, and we have two samples. And if you look closely, you can see that every gene has double its expression. So sample 1 has double the expression of each gene. Sample 2 has double the expression of each gene compared to sample 1. And this is a small data frame, so it's clear that there's this doubling that happens for each gene. But imagine if you had 10,000 genes. This might not be so easy to see. Which is why it would be nice to plot something like a heat map where you could qualitatively notice this doubling trend. But also notice the gene F has a much higher baseline expression value for both sample 1 and sample 2. So if we were to just naively plot a heat map for these data, we'd get something like this. Now this heat map unfortunately gives the impression that genes A to E have no significant difference in expression between sample 1 and sample 2. But we know that's not true. We know that sample 2 has double the expression for all of these genes. And it really just looks like gene F is the only gene that shows a big difference in expression. And that's because when we don't scale, when we just use the raw values, the heat map can get dominated by values that are just absolutely higher than other values. So what we can instead do is we can do this thing called z-scaling. And z-scaling simply means that we subtract the mean. So if we do z-scaling for the genes, we would subtract the mean expression and divide it by the standard deviation. And that's really easy to do in R, and we'll take a look at how to do that. And this is the output with that z-scaling. And so you can see that this heat map more accurately reflects this doubling of gene expression in sample 2 compared to sample 1. Okay, so that's a quick-fire introduction to hierarchical clustering in heat maps. So if we go to RStudio, so you can either go into a project that you have set up for this series of meetups, or if you don't have a project, you can just go into RStudio. I'm in my meetups project. So in the console, we type in remotes : install _GitHub Duke CCT/cbrg in quotes force equals true. And this will take a few seconds to run. And then we can just launch the package by typing in library cbrg. And to launch the script for today, we type in launch _project and 17. And so that launches the project RMD for today. And before we actually go through the code, we can, it's a good idea just to save the script. So to do that, you save as, and then you navigate to the directory folder, which is here. And so now if you make any changes to this, add your code or add notes, it will be reflected, it'll be saved in the project directory. As usual, we just run through the first chunk. So this will look to see if you have any of the necessary packages for today installed. And if you don't, then it will install these packages. So you can see that in addition to the tidyverse package, which we use almost always, we have a few other packages that we need for today. Specifically, this package called pheatmap, which stands for pretty heat map, which is what we'll be using to plot our heat maps. Before we move on to the code, I do want to say that much of the heat map code that is in today's session has been adapted from this really nice blog post by Dave Tang. And so I strongly recommend taking a look at that blog post and his website in general. If you would like to learn more about hierarchical clustering, because the details, there are quite a few details, here's a really nice 3-part series, Introduction to Hierarchical Clustering, by the statistics professor Roger Peng. And these are 3 15, 20-minute videos that nicely introduce this topic. So for today's session, we'll be using a data set called NCI60. And NCI60 contains microarray data for 60 tumor cell lines. And so to load that, and NCI60, the data set comes from this package called ISLR. So to load NCI60, you just do data NCI60. And unlike a lot of the datasets that we've used previously, so if we just click on NCI60 to take a look at it, unlike a lot of datasets that we've looked at previously, NCI60 is not a data frame. It's what's known as a large list. So this is a little bit fiddly. So what we will do is we will extract the necessary information from this large list and make our own data frame. And so one thing we can do with a list is to look at its kind of big picture, to look at its contents. We can use this function called names. And if we do names NCI60, if we look at the console, we see that there are 2 components of NCI60, data and labs. So data, as the name suggests, contains the microarray data, and labs are the labels associate other sample names. So the sample names indicate the cancer cell type. So to extract the labels, we can just run NCI60 $labs, and we assign it to this object called NCI_labs. So that's just the labels. And actually, we can just take a look at what NCI labs contains by typing it into the console. And you see that it's just a character vector of cancer type names. And similarly, we do the same thing for NCI60 data. We could run that. Actually, I will run that here. And we see that NCI data, so this is, it doesn't format so nicely. The format isn't so nice. But if we look at our environments pane, we see that it's a large matrix. So now we have split NCI60 into a character vector of sample names and a matrix. So before we use this information to make a data frame, we can just take a look at the size of our matrix, firstly. So the question is, how many genes and samples does NCI data contain? So we can run dim on NCI data, and we get 2 values. So dim can be, just as we can use it for data frames, we can also use it for matrices. So we see that the output is 64 and 6,830. So 64 corresponds to the number of samples, and 6,830 corresponds to the number of genes. The second question is, how many samples are there for each cancer type? So we will need to use the NCI labs object. And there are a few ways of doing this. One is to use this function we've come across before called table. So we do table NCI labs. And if we run that, we can see that we have the different cancer types along with the number of samples each cancer type contains. So there are 7 breast cancer cell lines, 5 CNS cancer cell lines, and so on. There's another really nice function within the tidyverse also called table, but it's spelled TABYL. And if we run that, and if we run that, we see that the output is pretty similar to the base R table, except we see that the format is nicer. So the output of this TABYL is a data frame, which is nice because we can then use that to do other things. And in addition to giving us a number of samples in each cancer type, it also gives you the percentage, which we won't use today, but that's nice to know. That might be nice to have. So line 79, it encourages us to plot these data, which is always a good idea. So we can use this table function on NCI underscore labs. And because table, TABYL, produces a data frame, we can just pipe it into ggplot. And so if we pipe this, on the x-axis, we put our cancer types. And on the y-axis, we have the number, which is just n. And we can use we can make a bar graph. So we do geom underscore call. And we see that we get this bar graph of the numbers in each sample. We can, just before we move on, we'll just quickly fix this. We can reorder the columns in descending order of number. It just makes it easier to see things. And to do that, you can just do that on the fly. So this NCI labs that's within this aesthetic function, you can put that within a reorder function. And you can reorder according to the number in each group. So if we run that, we get our bars in ascending size of height. And if you want it in descending side, you just do a -n. And one final thing that if you wanted to adjust, a lot of times, especially when you have long sample names or long names, is you can get this ugly overlap on the x-axis. So to do that, it's a pretty simple fix. We can use a theme function. We do theme axis.text.x is equal to element underscore text. And within element underscore text, you can specify an angle. So the default angle is 0. So we can specify an angle of 45 to get our labels, our x-axis text to be diagonal. And we can add one more thing. We can do this thing called vertical adjustment, this function, this parameter called vjust. And let's first take a look at when we set it to 1, which is the default. Nothing happens. If we set it to 0, we see that the x-axis text is now shifted so that it's no longer on the plot, which is nice, but there's a big gap between this x-axis text and the main plot. So we choose an intermediate value. I think 0.6 would be nice. Yeah, and so we get this nice plot. Okay, so that's now that we've got a little bit of a better sense of what NCI 60 contains, now comes the time where we convert it to a data frame. If we go back, if we do dim NCI data, we notice that here the the rows are the samples and the columns are the genes. So the first thing we can do is transpose that, make the rows genes and the columns samples. And that'll become clearer. The reason for doing that will become clearer in a second. So we go to line 86. To transpose a matrix, it's simple. You just do T and then the name of the matrix. And so we can run that and then just overwrite NCI underscore data. Then we convert that matrix to a data frame using as.data.frame. And now if we look at NCI data, which is a data frame, we see that the rows are genes. So for this example, this data set, I don't think it has gene names. So just for the purpose of today, we'll just consider these numbers to be gene names. But it does have sample names. Unfortunately, this NCI data frame as it is just has these unhelpful column names, V1, V2, and so on. So to assign the correct sample names to these columns, we can go to line 88, and you just do call names NCI underscore data, and then you just assign the contents of NCI underscore labs, which, as we know, contains the names of the samples. So if we run that and take a look at NCI underscore data again, we see that now we have a nice data frame of gene expression values, and each column has a nice sample name corresponding to the cancer type. So for today, we won't be looking, so there are, as you can see, there are multiple cancer types. For today, we'll just be looking at a subset of breast and colon cancer types. So line 90 asks us to only keep data for breast and colon samples. So this is a little bit tricky. And the reason it's tricky is because this data frame contains duplicate column names. So we can just see what happens if we naively take NCI data and then select let's say just breast. Let's see what happens. We get an error because it says that these names are duplicated. So I actually didn't realize that this was an issue because most data frames I've come across don't have duplicated column names. So one solution I tried was to use this helper function called contains. So contains just takes in a string. So I was like, okay, if I just use contains and I run this should work. It still doesn't work because R does not like, well, dplyr doesn't like that there are duplicate column names. So Paul came up with a nice solution of first piping in NCI data into this function called clean names. And this is from the janitor package that we briefly introduced in the previous session. So if we just run this and see what happens, actually we can just pipe this into another function called names just for now, just for this. We can see that it's converted all the names for one thing into lowercase, and wherever it's detected a duplicate, it's put an underscore 2 if there are two column names that are the same. It'll do an underscore 2 and 3 if there are 3 column names that are the same, and so on. So this way, it takes our duplicated column names and makes all the column names unique. Now it becomes easy to then use this, pipe that into the select function, and we can do first contains breast lowercase, and then again, since we also want the colon cancer type, we do contains colon, and we can just save this as a data frame called NCI underscore small. And if we look at NCI underscore small, we see we now have a smaller microarray data set and the columns, and it only contains information for the breast and colon cancer samples. So now we're almost ready to plot our heat map. This is, as you can see, NCI underscore small has 6,000, almost 7,000 genes. So just for the purposes of today, just to make it clear what the heat map looks like, we can just take a subset of these genes. One approach is to take, as is noted here on line 98, just keep the top 50 most highly varying genes. So how do we do this? This is surprisingly not that straightforward because the strategy we can use is to compute gene by gene the variance. And so what that tangibly means is we would take row 1, all the values in row 1, and compute the variance. Then we take row 2, compute the variance for all the values in row 2, and so on. That's actually easy enough to do in base R, this kind of what's known as row-wise computation. But dplyr is not especially good at row-wise, so-called row-wise computation. So for example, if we wanted to instead compute the variance of everything in the first column, breast, that's super easy. We've used the mutate function to do something like this before. So dplyr kind of naturally works on values in a column, not values in a row. So there's been a recent development in the dplyr world where they've introduced functions that allow you to do the same things that you do with dplyr, but across for each row as opposed to each column. So there's a lot to this, and this is worthy of its own session. But I will go through 2 approaches of doing this thing of like just keeping the top 50 most varying genes. I'll show first the dplyr way, and then show you the base R way, and then comment on why I'm even showing you 2 ways as opposed to just 1. So let's go through this line by line. We take our NCI underscore small data frame, and then if we want to do anything row-wise, we need to first specify that. And so we pipe it into this function called row-wise. And so this tells R that all subsequent computations need to be done across for each row as opposed to each column. We can then just use mutate to create a new column called vars. So vars will contain the variance values. And vars is equal to the var function. But within the var function, we have this other new function called c underscore across with nothing inside it. And the reason we have underscore across is because we didn't have it. So if we'd erase that, R doesn't know that we want to compute the variances across all the columns. So C underscore across with no arguments in it tells R that we want to compute the variance, in this case, across all the columns. And C underscore across stands for column across, so it's across the columns. And you can see that the default is the columns that it chooses are everything. So if you want it to be more verbose, you could just specify calls is equal to everything. And I appreciate that I'm introducing a lot of new things here, but hopefully this makes some sense, and the base hour way should hopefully make even more sense. All right, so if we run just those lines up to the mutate, this will compute the variances for each gene. What we then have to do is we need to ungroup this. Why? Because this row-wise function on line 100 is a grouping function. So since we can only want to keep the top 50 most highly varying genes, we have to do this switch now from row-wise back to column-wise. And to do that switch, we have to first ungroup. And then on line 103, we can use our familiar arrange function to arrange this data frame in descending order of the contents of vars, so in descending order of variance. And then we can use slice to specifically keep the first 50 rows. So slice 1 to 50 keeps the first 50 rows. And then we just want to get rid of this vars column because we don't need it anymore. So that's a lot. And if we run all of this, we get this thing called NCI. We can assign it to an object called NCI underscore top underscore 50. And if we take a look at that, we see that it has the same number of columns as the previous data frame, but it only has 50 rows. And these are the 50 most highly varying genes. One thing to note is this, this is fine, but I'll actually just run this again. And you see that this isn't an especially big data frame, but it still takes a few seconds to compute. So that's the problem with dplyr, is that once you start to get to bigger numbers, in the thousands or tens of thousands, dplyr can become really slow. So the alternative is to do the base hour way. So to do that, we can use this to compute the variances for each row. There's a function called row vars. And this comes from one of the packages we installed today, matrix stats. And row vars, we can try to apply it directly on NCI underscore small and see what we get. And we see we get an error because it says that argument X must be either a matrix or a vector. So that's easy enough. We can just do as.matrix. And we can run this. And now we see that we have basically a long numeric vector of variances. How do we use this to get the top 50 most highly varying genes? One step is to, so actually before I get to this, so what we can do is we can use this other function called order. And if we run this, we now get, and this is a little bit difficult to explain, but these are the indices of the how do I explain this? Let's take a simpler example. Apologies for this. Let's say we had a really simple vector, A with, 400, 300, 100, and 200. Now let's say we wanted to order this from lowest to highest. So 100, 200, 300, 400. How would we do that? Well, one way, let's build up to that. How would we select the smallest element of A? Well, we could do A, and we know that the smallest element is 100, so that is 1, 2, 3, the third object. So if we do A subset 3, A subset 3, we get 100. How do we pick the first two elements? So in order, 100 and then 200. We can do, within the C function, we can do 3, 4, because 200 is the fourth element. So now we get 100, 200. How do we get 100, 200, 300? We do subset on 3, 4, and then 2, because 300 is the second element. And finally, we can just do 1. And so we see on line 110, we can use this subsetting approach not to subset the original, in this case, vector, but to rearrange the elements of the vector. So now we've ordered it in ascending order of size. Alternatively, we can use this function called order. So if we do a square brackets order a, we get the same output as before. And that's because what order has done, so if we just take a look, order a, it just gives you the index of, so what it means is, so here it gives you 3, 4, 2, 1. That means the fourth element is the smallest because it has a 1. The third element is the second smallest because it has a 2. The first element is the third smallest, and so on. And if we wanted to order it from highest to lowest, we can just specify this decreasing parameter to be false. And now if we subset A, instead of going from 100 to 400, we go from, instead of going from, decreasing is equal to true. Now instead of going from 100 to 400, we go from 400 to 100. So we can get this reordering of a vector. And just as we can reorder a vector, we can also reorder a matrix or a data frame using this order function. So first, let's get these ordered indices. So if we go to line, in this case, 115, and recall that we have to specify decreasing is equal to true because we want the highest variance down to the lowest variance. We get this NCI underscore order. And so this NCI underscore order, if we just take a look at that, this is just a numeric vector of indices, which we will use to reorder our NCI underscore small data frame. And to do that, you just do NCI underscore small, square brackets, NCI underscore order. And since we're reordering the rows, we do comma. And then after the comma, we just we do nothing because we want the columns to be in their original order. And if we run this, we get NCI underscore small with the first row corresponding to the gene with the highest variance, and then decreasing variance as you go down that data frame. And we only want to keep the first 50 elements, so that's easy. We can just take NCI underscore small and then subset it, do 1 to 50, 1 to 50, comma. And it says to convert this to a data frame. That's easy. We do as.data.frame. And we can assign it to this object called NCI underscore top underscore 50, just as before. Notice that when we ran these 3 lines, it just took milliseconds to compute. What took dplyr a few seconds to compute. So that's one reason to, in this case, use these base R functions. So order is a little tricky to certainly to explain, but if I would encourage you to play around with some simple vectors and matrices to see how it works. And so one small note about why we've decided to pick the 50 most highly varying genes. I've put that note here. I won't go through it, but this is something that you see a lot. People, if they have to select a sample of genes, they often pick the most highly varying genes. And I've put the text for why I think this is the case on these lines here. Anyway, we're now ready to actually make our first heat map. And so to do that, if we go to line 132, we can use this function called pheatmap. And we can just give it NCI underscore top underscore 50. And if we run that, we straight away get a really nice, what looks to me like a really nice heat map. It has a dendrogram for the genes, it has a dendrogram for the columns. Recall from the kind of lecture component that it is encouraged, it is recommended that we use scaled values to plot our heat map. So to do that, there are 2 ways to do it. One is to actually scale the input data. And to do that, we can use this function called scale. And if we look at the help section, it says scale is a generic function whose default method centers and or scales the columns of a numeric matrix. So notice that it works on the columns. But we want to scale our genes. So to do that, working inside out, we can first transpose our NCI top 50 so that now the columns are genes. We can apply scale to this. And then we need to transpose this output again to go back to our original shape of having the rows be genes and the columns be samples. We can assign this to this object called NCI underscore top underscore 50 underscore scaled. And just to check that this has worked, so this scaling is known as Z scaling. And as I mentioned previously, this involves subtracting the mean and dividing by the standard deviation. And so what this means is that the row means, the means of each of all the genes, will be 0. And so we can confirm that by just doing row means and just looking at the first few values, and we see that they're almost 0. And what z-scaling does is it forces the standard deviation to be 1. So similarly, just as we have row means, there's a function called row SDS. And if we run that, we can see that they're all 1s. So we can confirm that our scaling was done correctly. Now when we plot the heat map on the scale data, we get something that looks pretty similar to the previous one. Well, actually, no, it does look quite different. So this is the output of using scaled data for the heat map. Fortunately, pheatmap has a parameter that allows you to scale on the fly. So you can just do pheatmap NCI underscore top underscore 50 and just do, I believe it is scale is equal to, you need to specify what you want to scale. Do you want to scale the genes or do you want to scale the columns, the samples? I want to scale the genes, so I specify scale is equal to rows. I think it's scale is equal to row. Yep, and you can see you get the same output. So this is nicer because you avoid having to compute the z-scores yourself. For the kind of final part, we'll just take a look at some of the sort of fancier features of pheatmap. One thing we can do is we can annotate the rows and we can annotate the columns. And I will show you what that means in a second. So one thing we can do with the rows is, let's say we had some additional information about these genes. Like some of the genes are associated with pathway 1, other genes are associated with pathway 2. So we could add that as a color component to this. We don't have that information here, so instead what we'll do is we will assign the genes to 2 clusters. And we'll compute those clusters using hierarchical clustering. And so to do that in R, we can go to line 150. Going inside out, we first need to compute the distances between our genes. And so that's just like what we saw in the lecture component on the slides, where we saw that we first need to compute the Euclidean distances. So that's what this dist function does. And then we can use these distances as input to hclust. And hclust is the base R hierarchical clustering function. And we need to specify a method. This is the linkage method that we spoke about a little while ago. We can specify that method equals complete. So if we run all of this and we assign it to an object called myHclust gene, if we just run that object myHclust underscore gene, we don't see anything. Give me 1 second. Oh, okay, so this is just computing the, this is just the hierarchical clustering output. To visualize this, you can use this as.dendrogram function, which takes this my underscore hclust underscore gene object, and you can specify that you want it to be horizontal by piping it into plot horizontal equals true. And we see that we get a dendrogram, and it's hard to see because there are 50 genes, but you can see that this is how the genes cluster. And you can see that there are 2, they kind of coalesce into 2 big clusters. How do we now specify, assign cluster membership to each of these genes? We can use this function on line 157 called cuttree, C-U-T-R-E-E. We give it a dendrogram, so this one, and we specify the number of clusters we want, 2, so k equals 2. We can assign this to this object called my underscore gene underscore call. And if we take a look at that, we see now that each gene belongs to one of two clusters, one or two. We can convert this into a data frame. So if we want to annotate our pretty heat map, takes in a data frame of a certain format. So let's make that data frame for the rows. So if we run line 162, and this is an easy way to make a data frame, we just do data.frame. This data frame currently contains only one column. You give that column a name, cluster underscore ID, and then give it the cluster information. If we look at this resulting data frame, we see that it's just a data frame of clusters. Now we need to do one more thing. Notice that the row names here are just 1, 2, 3. We need to specify the row names of this data frame have to be equal to the row names of this NCI top 50, which we use to make our heat map. And so to do that, that's really easy. We go to line 167, we do row names, this myGeneDF, and we take the names from the myGene call, right? So if we just do names myGene call, these are our gene names. We can assign those to the row names of this new data frame. So now when we take a look at myGeneDF, we see that the row names are the genes, and it has just this one column called cluster, which tells you if the given gene belongs to cluster 1 or cluster 2. Now that we have this data frame in the right format, we can add that as an additional argument to our pheatmap, so line 170. So the parameter is annotation underscore row, and then it's equal to this argument, my underscore gene underscore df. If we run this, we get this output. And this is what I mean by annotating. So now we have these colored squares, rectangles, that tell you if a given gene belongs to cluster 1 or cluster 2. Similarly, we can annotate our samples. And so we can specify if each sample, if it belongs to either the breast group or the colon group. So to do that, we need to come up with just like we had this data frame for rows, we need to have for annotating the rows, we need to have a data frame for annotating the columns. So again, we just need to come up with create a one column data frame that tells you if a given sample belongs to breast or the group or belongs to the colon group. So to do that, we can actually just use the column names of this NCI top 50 scaled. And so these are the column names. And we can extract just the name breast or the name colon from these sample names. And to do that, if we go to line 176, I will skip some of these details because it's easy enough, I hope, to work out. So if you just, for example, take this str remove and what's inside it and run that in the console, you see that you've converted this input into this input. So now instead of having, breast underscore 2 underscore 3, you just have the group name. And if this / underscore looks a little bit strange to you, we covered this in our previous session. So this is using what's known as regular expressions. So we use all of this to create a data frame called my underscore sample underscore call. And let's take a look at that. And so we can see here we have just a column called tissue. And it tells you if a given sample belongs to the breast group or the colon group. Again, just like with the gene annotation, we need to ensure that the row names for this data frame are these here. So breast underscore 2, breast underscore 3, and so on. So to do that, that's again simple enough. We just do row names, my sample call, and then we extract the column names from NCI top 50 scale. So to see that, we can just run that in the console. So if we run line 181 and then take a look at my underscore sample underscore call again, we now see that the row names are the sample names and the column, this tissue, is the group that each of these samples belongs to. So now we're ready to add that to our pretty heat map as an column annotation. So that's on line 186, and we get this. So now you can see that we have these nice purple or blue rectangles that tell you which tissue a specific column belongs to. Just a couple of more things, and when we're done for today. Again, we're just scratching the surface of what Pretty Heat Map can do. It's really powerful, and you can make all kinds of sophisticated maps. So we can see here that we have two sample groups, and by definition, we've created two gene clusters. We can actually put a little gap, just for aesthetic purposes, a little gap between these two clusters. And so to do that, if we go to line 191, we can see we have two additional parameters, cut tree rows and cut tree columns. So if we do cut tree equals 2, actually, I take that back. If we do cut tree rows equals 2, it will split our rows according to the two clusters computed by the hierarchical clustering. If we do cut tree calls equals 2, it will also perform hierarchical clustering, but on the samples, and split the samples into two clusters. So this might be informative. Like, so that you can see that these 4 breast cancer tissue samples kind of form their own cluster. So it's kind of interesting that they're separate from these 3 here. So that might be informative. But either way, you get these nice gaps here, which might be aesthetically pleasing. One final thing that we can do is, let's say, so this is, we just have 50 genes, but if we had all our genes, almost 7,000, this dendrogram on the left would be really big and might take up too much space, might not even be that useful. How do we get rid of it? We can do that here. So line 203, we can just set this tree height row parameter to be equal to 0. And if we run that, we get rid of the dendrogram. And if you want to learn more about pheatmap, you can just look at its help section. And you can see that it has like 50. It has tons of parameters. So that's it for today. I hope you enjoyed that, and I hope to see you next time. Thank you.